Lab 6.4. So in the last class, we were talking about present value of an annuity, and we were given the present value of an annuity formula. A equals R times 1 minus 1 plus I to the negative nth power divided by I. In this formula, it tells us if we have some large lump sum of money, A, we can get payments of, if the account pays I% per period for N periods, then R tells us basically the size of the payments we can get from the account over N periods. So you start with some large lump sum of money, and we were saying we'll take money out of it. And then we also said that if you look at it from the other point of view, if you're borrowing money, if you borrow a large lump sum of money, that money plus the interest that will accrue over the period of the loan would be the large lump sum. And then the R would represent the payment amounts that you pay to pay off the loan and the interest. All right. So for problem number 1 here, it says, what is the present value? So how much money would you need right now in order to receive semi-annual payments of $5,000 for 10 years, assuming that you are earning 5% interest compounded annually? So we're asked to find A here. In the formula, R would be the size of the payments. So that would be 5,000. And then be careful for your I and your N. I is the interest rate per period. 5% interest compounded annually, that's semi-annually, that's 0.05 over 2, which would be 0.025, 2.5% per every 6 months. And then for N, it's the number of periods over the entire loan. If we're compounding semi-annually, or we're getting semi-annual payments, that's twice a year. For 10 years, 2 times 10 would be 20. And then we plug all of this into our formula. A equals 5,000 times 1 minus 1 plus 0.025 to the negative 20th power divided by 0.025. And remember, when you're doing these problems, I'll be looking for this, the formula that you used and what numbers you plugged into the formula. And from here, you can simplify and however many steps you need to, 1 or 2 or 5, it doesn't matter. I do recommend trying to do it step by step instead of trying to put everything into the calculator at once. That'll kind of minimize your possibility for errors. And if you do more steps, I can see what you did step by step and give you more partial credit. All right, let's simplify the numerator here. 1 minus 1.025 to the negative 20th power. Okay, this would be 5,000 times 0.389729057 divided by 0.025. So that's 5,000 times 15.58916,229. And then finally, the lump sum that we need would be $77,945.81. We round our last number 2 decimal places to the nearest cent. So what does this mean? This is saying that if I take $77,945.81 and I put it into an account now, and that account earns 5% interest compounded annually, I will be able to take out $5,000 every 6 months for 10 years. Okay, so I end up getting 5,000 times 20. I'll end up getting $100,000 out of the account, and that's from the $77,945 that I put in, plus the interest that that money earns while it's sitting in the account. All right, problem number 2. How much would you need to save up for retirement if you plan to live off of $2,500 a month for 15 years, assuming your investment earns 7% interest compounded monthly? Okay, so this is another one where we're trying to find A. In this case, R, the amount of the payments we're receiving is $2,500. What else do we need? I, I is the interest rate per period. So that's 7% monthly. So 7% divided by 12. Does that simplify nicely? 0.07 divided by 12. No, you get a repeating decimal, 0.00583 repeating. And then N would be, we're doing this monthly for 15 years. So 15 times 12, which is 180. That gives us A equals 2,500 times 1 minus 1 plus 0.07 over 12 to the negative 180th power divided by 0.07 over 12. Now, when you're simplifying this, again, you can take it step by step, try to simplify the numerator that's in the brackets first, and then divide by the denominator. So let's see, the numerator, 1 minus parentheses, 1 plus 0.07 over 12, close my parentheses and raise that to the negative 180th power. All right, that's 0.648993086. We're going to divide that by 0.07 over 12. When you're dividing by a fraction, make sure you put that fraction in parentheses. So my calculator, I'm typing in divided by, open parentheses, 0.07 divided by 12, close parentheses. And this gives me 111.2559576. Multiplying this by 2,500, our answer would be $278,139.89. Then on to problem number 3, which it looks like we set up a little bit here. It says you plan to take out a $700,000 mortgage for 30 years with monthly payments. That's a pretty standard loan period, 30 years, and you pay your mortgage monthly. When you take out a loan, especially for a mortgage or like a car or something, as I mentioned before, you have to pay that money back. Obviously, you're borrowing it from the bank. And then you also have to pay interest on however much you owe each period. So it's essentially a present value of an annuity problem, except you have money that you owe. As long as you owe that money, you have to pay interest on it. So every period you pay a little bit on it, but then you still owe interest on what's still there. It's the opposite of what we were doing before. Before it was the money is in the account, and as long as the money is in the account, you earn a little bit of interest. Well, now, as long as the money is sitting in the account and you owe the bank that money, you have to pay more money on it because interest is now something that we're paying. But all of that's put together, and then your loan amount, your monthly payment is calculated based on how much money you borrowed, how long it's going to take you to pay off the money that you borrowed, and then how what your interest rate is. All of those things are put together. All right, so in this example, R is what we're trying to find. We know A is 700,000. And then what's missing? Oh, N. We're taking out this loan for 30 years, and we're making monthly payments. So altogether, there will be 630 mortgage payments. So we get 700,000 equals R times 1 minus 1 plus 0.07 over 5. I'm sorry, 0.057 over 12 to the negative 360th power divided by 0.05 over 12. We need more room. All right. So this would be, if we simplify the numerator, 1 minus parentheses 1 plus 0.057 divided by 12 raised to the negative 360th power. Did I type this in right? Okay. 700,000 equals R times 0.818405. Let me just double check my math. Yeah, that looks right. And then divide it by parentheses 0.057 over 12. $700,000 equals R times 172.2948421. And then we need to divide 700,000 divided by this 172 decimal. That equals R, which would be $4,062.80. So this is saying if you take out this mortgage for 30 years at 5.7% interest and we're compounding monthly, this is if you don't put a down payment down at all. That means you don't pay any money up front. Your monthly mortgage payment will be $4,062.80. All right. So for 3B, it's a similar situation, except we're told that we make a down payment of $20,000. That means you pay $20,000 in cash up front, and then you only have to borrow $680,000 from the bank. So now when you calculate this, A is going to be equal to $680,000. Everything else, oh no, our interest rate went down. So if you put down a down payment, your interest rate goes down a little bit. So now I is 0.052 over 12. Does that simplify better? 0.052 over 12? No, okay. And then N is still 12 times 30, which is 360. All right, let's calculate what our payment would be in this case. If we pay $20,000 up front and our interest rate goes down a little bit. If you think about it, you're borrowing less money and the interest rate is lower, so the payment should be lower. So we can expect a lower number than what we got for part A. We'd have 680,000 equals R times 1 minus 1 plus 0.052 over 12 to the negative 360th power divided by 0.052 over 12. All right, simplifying the numerator. 1 minus 1 plus 0.052 over 12 raised to the negative 360th power. That's 0.7891545519. And then divided by 0.052 over 12. We have 680,000 equals R times 182.1125814. And then if we divide 680,000 by this number, we get $3,733.95. All right, so if you take out this $700,000 mortgage, if you don't put a down payment down at all, you get an interest rate of 5.7%. Your mortgage payments end up being $4,062.80. If you can put $20,000 down, your interest rate will get lowered to 5.2%, and then that'll make your monthly payments get lowered to $3,733.95 a month. And the problems that we're going to look at today are going to be a little bit similar to this. And we're going to additionally break down how each of these payments go towards paying off the principal, the amount that you borrowed for the loan, and paying off your interest. That's what an amortization table is. So this is an example of a loan problem that we're modeling using our present value of an annuity formula. We're going to do more problems like this and then also break down what each payment goes towards. Because remember, when you make these payments for your loan, you're paying off the amount that you borrowed originally, plus the interest that accrues. So we're going to break down step by step exactly which part of your payment goes towards the principal and which part of your payment goes towards the interest. Loans and amortization. Okay, loans are usually paid off by a series of partial payments with interest charged on the unpaid balance at the end of each period. This type of loan is usually repaid by making all payments, including the principal and the interest, of equal size. The process of repaying the loan is called amortization, okay? What's happening here is basically the bank is purchasing an ordinary annuity from the borrower that pays a fixed return each payment period. So you can think of the payments that you're making as annuity payments and the present value of an annuity type of situation. It's annuity payments that you're making to the bank, but the payments represent you paying back the loan and the interest on the loan. All right. Question, does this look familiar? It should. We just used it 4 times for the last few problems we did. What is it? This is the present value of an annuity formula. And what variable represents the payment in this formula? That would be R. R represents the payment in the present value of an annuity formula. So for our loan formula, we want to solve for R. So take this formula, the present value of an annuity formula, solve for R. If we do that, we just get A times I over 1 minus 1 plus I to the negative n. Okay, so if you take your present value of an annuity formula and solve for R, that is the loan or amortization formula. Essentially, they're exactly the same thing. In one, we're solving for the large lump sum that we got, A, and the other, we're solving for R, the amount of the payment. Okay, so this formula, which is the exact same as the present value of an annuity formula, except we're solving for R, is our loan formula or the amortization formula. Okay, so we're going to use this formula to determine the amount of our payments when we take out a loan. We need to know the interest rate and then our compounding frequency, and then also how long it's going to take us to pay back the loan. Okay, if we know all of that information, we can figure out the amount of the payment. Example 1, page 414 in your book, if you have your book. A debt of $1,000 with interest at 16% compounded quarterly is to be amortized by 20 quarterly payments over the next 5 years. What is the size of the payments? Okay, so in this case, we're being asked to find the size of the payment. That's R. What are we looking for? The amortized payments. What do we know? I don't like the way it's broken down here, so I'll write it up here myself. What do we know? We know a lot of good stuff. First, we know that we are making 20 quarterly payments. So isn't that nice of them? They tell us what N is. N is equal to 20. We know that the interest rate is 16% compounded quarterly. So I would be 0.16 over 4, because we're compounding quarterly, which is 0.04. So 16% for the year would be 4, compounded quarterly would be 4% each quarter. And then what else do we know? That's all the stuff that we know. All right. If we plug all of these things into our formula, oh, I missed the A. Sorry, you guys. We also know that we borrowed $1,000. So we borrowed $1,000. Our interest rate is 16% compounded quarterly, so that gives us an I of 4% or 0.04. And then we're told how many quarters we have. We're making 20 quarterly payments to pay this off. So N is 20. All right, all we're gonna do now is plug all of these things in. As I mentioned the last few classes, when you're doing these types of problems, your first 2 battles are, you need to be able to read the problem and determine what type of problem it is. Is it present value of an annuity? Is it future value of an annuity? Is it a regular compound interest problem or a continuous compound interest problem or a simple interest problem? So look for keywords that tell you what kind of problem you have. And then from there, being able to figure out these values of I and N. Once you have those things, it's just a matter of taking your time to simplify the formula. All right, so if we plug this in, we get 1,000 times 0.04 divided by 1 minus 1.1 plus 0.04 to the negative 20th power. And then, of course, we want to simplify that step by step. I would simplify the denominator and then do 0.04 divided by that number and then multiply by 1,000. So I would do it in 3 steps. Or you can do it in 2 steps, like what's done here. Simplify this part first and then multiply by 1,000. When you're typing the part in the brackets into your calculator, if you wanted to type it in all at once, you would do 0.04 divided by, open parentheses, so put your entire denominator in parentheses, 1 minus parentheses 1 plus 0.04 to the negative 20th power, and then close your parentheses again. Your entire denominator needs to be in parentheses in order for your calculator to calculate this correctly. Take a moment to try to type that in. So type in the part in the bracket and see if you get the same decimal that's here. 0.04 divided by parentheses 1 minus parentheses 1 plus 0.04, oops, to the negative 20th power. Yes, I got that same number. And I know you might be thinking, I know how to type stuff into a calculator. I don't need to practice. Please practice. Make sure you practice. All right, so this simplifies to about $73.58. So what is this saying? The payments on the $1,000 loan at 16% interest compounded quarterly for 5 years is $73.58. Now, when we're doing the problems today, I want us to remember that in these cases, interest is bad. Before we were talking about getting payments out of an account or investing into an account. And then if you're making an investment, interest is great. It's free money that you're getting. When you are taking out a loan, interest is bad. That's extra money that you're paying for borrowing this money. The longer that it takes you to pay back the loan, the more interest you end up paying. And then in this case in particular, let's see how much we end up paying on this $1,000. We are making quarterly payments of $73.58. If we take for 5 years, $73.58 times 20. So a little extra note here. $73.58 times 20 payments. You would end up paying back $1,471.60. This is the amount paid back. So if you make these quarterly payments for 20 quarters, you actually end up paying $1,471.60. How much money did you borrow? You only borrowed $1,000. So you're paying an extra $471.60 in interest. That's just free money you're giving away. Well, you had to borrow the money, so it's not, I'm sure you had a reason to need to borrow it, but little note here, you pay $1,471.60 minus $1,471.60 in interest. And think about these things like when you're making any kind of loan payments, so student loans and car payments and all of that. The higher your interest rate, the more interest you have to pay. And also the longer you take out the loan, the more interest you'll end up paying. Keep those things in mind. All right, one problem down. For example 2, a man buys a house for $200,000. Good job, man. He makes a $50,000 down payment and agrees to amortize the rest of the debt with quarterly payments over the next 10 years. If the interest rate on the debt is 12% compounded quarterly, A, find the size of the quarterly payments, B, find the total amount of the payments, and then C, find the interest that he ends up paying. All right, I like this problem. So again, we have something like a mortgage or a car payment. Sometimes we borrow, there's a price, or let me take it back. The price of the home or the car is given. Sometimes we have some cash that we can pay up front. That's a down payment. So in this case, this house is $200,000. This man has $50,000 in cash that he's going to pay up front. The rest of the money is what he's going to borrow. So the first thing you need to do here is figure out how much you need to borrow, which is an easy subtraction problem. What are we looking for in part A? So for part A, we're trying to find the size of the payments. We're going to use our loan formula. R equals A times I over 1 minus 1 plus I to the negative nth power. We just need to figure out what I is, what N is, and we're given A, or we can find A, the amount that we're borrowing. All right, let me skip through some of these parts. All right, the good stuff. What do we know? A would be equal to 200,000 minus 50,000. Because we're paying 50,000 up front, so we really only need to borrow $150,000. What? I need to edit this because it's bothering me. I don't want any of those numbers. We know A. I'm just going to ignore the rest of these for now. That's good to know. The next thing we need to know is I. I'm going to scroll up a little bit. It was 12% interest, compounded quarterly. So we're making quarterly payments. Our interest rate is 12%, and we're doing this for 10 years. So we're going to use that information to find I and to find N. Quarterly payments for 10 years, and then 12% interest compounded quarterly. Where was I writing this? Down here. So I would be 0.12 over 4, which would be 0.03. 12% interest compounded quarterly would be 3% interest each quarter. And then N, if we're compounding quarterly for 10 years, that would be a total of 40 payments that are being made. All right, now we have all of this stuff. We can plug it into our formula to find to find R. Here we go. $150,000, I is 0.03, N is 40. Plugging this information in, we get 150,000 times 0.03 divided by 1 minus 1 plus 0.03 to the negative 40th power. Be careful with these problems. Don't forget that negative in the exponent. Again, start off by simplifying what's in the brackets and then multiply it by your value of A. Take a moment here to practice this. Practice entering this into the calculator and seeing if we get the same decimal. 0.03 divided by parentheses. Remember to put your denominator in parentheses. 1 minus 1.03 to the negative 20th power. Oops, negative 40th power. Yes, I got the same thing. 0.043262378. And then we're going to multiply that by 150,000, the amount of money that we borrowed. And it gives us $6,489.36. All right, so this tells us the amount of our quarterly payments that we're going to have to make, or that this man is going to have to make. So he bought a $200,000 house, paid $50,000 up front, and then borrowed $150,000 from the bank at an interest rate of 12% compounded quarterly. He wants to pay this off in 10 years. So he's going to have to make quarterly payments of $6,489.36. All right, now the fun part, I think. We get this number. It's like, okay, so this guy's paying $6,400 a month or a quarter for his mortgage. Parts B and C, I think, are really interesting because that really helps you break down and see like, oh, how much money are we actually paying in interest here, right? So part B asks to figure out how much money do you end up paying back? We know he borrowed $150,000. If he makes 40 payments of $6,489.36, how much does he actually end up paying back? All right, so for part B, we're looking for the total amount of the payments. What do we know? We know R, the amount of the payment, and N, which is the number of payments that you're making. All right, so if you multiply these two things together, R times N, $6,489.36. That's the amount of the payment, times 40, the number of payments that you're making. He's going to end up paying back $259,574.40. All right. So once you know your payment amount, multiply your payment times N, and that tells you the total amount that you end up paying back for the loan. Remember, that's going to include the amount that you borrowed and the interest. All right, now my favorite part. So how much interest is this? How much did he actually borrow from the bank? So in part C, we're trying to figure out how much interest was paid. What do we know? We know the total amount that he ends up paying back, $259,000. That's what we found in part B. And we know the original amount that he borrowed. So the total payments and the total borrowed. If we subtract those two things, that'll tell us how much interest was paid. All right, so the total interest is going to be the total amount of the payments minus the total amount that you borrowed. Write that down. And hopefully that makes sense. It's pretty intuitive. If we subtract those things, that's a typo. Where's my pencil? It's fine. So this would be $259,574.40. That's how much your payments total up to, minus the original amount borrowed was $150,000. So there's a little typo here, but the answer is correct. $150,000 okay, and if you subtract those, $259,574.40 minus $150,000 leaves us with $109,574.40 in interest. So you only borrowed $150,000, but you end up paying back that $150,000 plus another $109,000 in interest. That's a whole lot of interest. It's a pretty high interest rate. All right. Before we go on to part 3, again, let's think about how we did this problem. We were able to use the loan formula to find R, the amount of the payment. Once you know the amount of your payment, to find the amount, the total amount that you pay back, you take the amount of the payment and multiply by N, the number of payments. You can make a little note of that somewhere. There's some room. So a little note. Total payment, we computed that by taking R, the amount of the payment, and multiplying it by N, the number of payments. And then to find the total interest, you'll take the total payment and you want to subtract off the total amount that you borrowed. All right. Now that we know how to do those two things, and we've done that a couple of times in other problems, we just weren't asked to. I always just take that extra step. Let's go on to problem number 3. It says Chuck and Ginger have $30,000 saved for a down payment on a house. Their budget will allow them a monthly mortgage payment of $1,200. What is the most expensive house they can afford to buy if they borrow money for 30 years at 7.8% interest compounded monthly? So this was an interesting one because we're not being asked to find the amount of the payment. We're being asked to find basically how much can they afford to borrow, right? We're told the amount of the payment already. They can only pay $1,200 a month. We're told the interest rate and the compounding frequency, 7.8% compounded monthly. And we're told that they're going to be doing this for 30 years. So using this information, we're able to figure out exactly how much money that they can borrow. Oh, and we're also told that they have $30,000 in cash. All right, so let's put all of this information together. What are we looking for? The cost of the house, or the maximum cost that they can afford to borrow. Okay, what do we know? We know all kinds of stuff. R, so I don't like when we use R, big R and little r, but that's how our book writes it. Little r would be the interest rate without, like, per year, without the compounding frequency. I just would rather us write it as, hold on, let's get down here. I and N. This is what I like to write it as. So we are told that we have 7.8% interest compounded monthly, right? And just to be clear, we'll go back up to the problem. Let's just write it out here. 7.8% interest compounded monthly. I would be 0.078 divided by 12. And then for N, we're compounded monthly for 30 years. So how many payments will that be? If you make monthly payments for 30 years, 360 payments. And then we also know capital R, the amount of the payment. We know that they want to pay, not $1,300, $1,200 a month. So that's information that's all given to us here in the beginning of the problem. And we are going to take into account that $30,000, but later on. Okay. So using these values, I didn't simplify my I. 0.078, let me double check this. 0.078 divided by 12 does equal 0.0065. Okay, so that's I, we have our N, we remember R is equal to 1,200. Let's plug all of this information into the formula. Now notice here, we're using the present value of an annuity formula instead of the loan formula. What's the difference? They're exactly the same thing, except in one you solve for A and the other you solve for R. So if you're looking for the large lump sum, then you would want to use the one where A is solved for. If you're looking for the payment amount, you want to use the loan formula where R is solved for. It doesn't really matter though. You can use one or the other, you'll always get the same answer, the correct answer, if you plug in the right numbers. All right, so in this case, we'd have 1,200 times 1 minus 1 plus 0.0065 to the negative 360th power divided by 0.0065. Simplifying what's in the brackets gives us 138.9138739. And then finally, if we multiply this by 1,200, this tells us that they can afford to borrow from the bank $166,696.65. But this does not answer the question completely. So what does this number tell us? This number tells us how much money they can afford to borrow from the bank. But we also know that they can put down a $30,000 down payment. So we want to take that into consideration too when we're thinking about how much house they can afford, right? So this doesn't tell us how much house they can afford. We need to add the down payment to this amount. If we add the $30,000 down payment, they can afford a house that is $196,697.65. All right, so this one was interesting because we were told how much they can afford to pay. We were given the interest rate that they got, and we're told that they're making monthly payments. From this information, we were able to figure out the amount that they're able to afford to borrow from the bank. And then when we take into consideration also the down payment, add the down payment to that, and that can tell you how much they can afford to buy altogether. All right. Last thing we want to talk about, because I mentioned earlier we were going to do this, is an amortization schedule. This breaks down in a table how each of your payments go towards your interest and go towards your principal. That's the original amount that you borrow. Okay. The idea, though, with these types of problems is once you take all of your payments and add them up together, it should be equal to the interest amount plus the principal, the amount that you originally borrowed. Okay. So an amortization schedule. This is a table that shows how a loan is reduced each period. So it tells you again how much goes to your principal, how much goes to your interest. We're going to do an example of this. The amortization schedule for a $10,000 loan with an interest rate of 10% being paid off in 5 equal payments. Before we do this, it's saying we're paying off for 5 equal payments. It doesn't say compounded annually, but that's kind of implied here. So we can figure out what the value of R would be. In this case, if we wanted to find R, we know A is 10,000. We're borrowing $10,000. The interest rate is 10% per period, so that's 0.10 because we're compounding annually here. And then we're doing this for 5 periods. So N would be 5, or 5 payments we want to pay it off in. All right, so R would be equal to 10,000 times 0.10 divided by 1 minus 1 plus 0.10 to the negative 5th power. Let's calculate that. 0.10 divided by parentheses 1 minus 1.10 raised to the negative 5th power. All right, if we multiply that, all of this together, we get $2,637 and about 97 cents. So in order to do this, if we wanted to pay back $10,000 at an interest rate of 10%, we want to pay that off in 5 equal payments. Okay, we need to pay back $2,637.97 each payment. Now, if you multiply that number by 5, $2,637.97 times 5, that's $13,189.85. So you end up paying more than the $10,000 because you're paying that $10,000 plus the interest. Next, we're going to look at exactly how this payment amount is broken down. All right, so notice this number, the amount of the payment. Notice where that is in the table. So you're going to break this down by the number of periods. Each period has its own row, okay? We have 5 periods because we're making 5 payments. The payment amount is always the same, $2,637.97, okay? But when we're paying that payment, we pay the same amount every month. It doesn't change for us. Where that payment goes does change. Part of the payment is going to go towards interest, and part of the payment is going towards reducing the balance of the loan. So this is basically saying every period that you have the money in the account, or however much you still owe, I'll say it that way, you have to pay interest on it. So when you first borrow the $10,000, you have to pay 10% interest on $10,000. Okay, what's 10% interest on $10,000? $1,000. Okay, so this number is found by taking the unpaid balance and you're going to multiply that by 10% because that's the interest rate. And that tells you how much money in interest you have to pay. You have to pay interest on your unpaid balance, and you're always going to pay 10% of that. Okay? So from your payment of $2,637.97, $1,000 of that has to go towards interest. The rest of it will go towards paying down the $10,000. So the rest of it, which is $1,637.97, that goes towards reducing the balance, okay? So how do we figure out the unpaid balance after the first payment? The entire $2,637.97 won't get subtracted from the $10,000 that we borrowed, only this amount. So the unpaid balance would be the amount that you owe for that period, or your balance going into that period, I should say, minus the reduction in balance. So here we took the 10,000, subtract off $1,637.90. That leaves you with $8,262.03. What does this mean? After your first payment of $2,637.97, your balance goes down by only $1,637.97. The other $1,000 goes towards interest. All right, so going on to payment 2. Our payment amount is still the same, but now going into payment 2, our unpaid balance is $8,362.03. So if we pay 10% interest on that, that's $836.20. And then now you just do subtraction. This number would be, okay, I should write it up here at the top. For the balance reduction, it's going to be your payment minus the interest every time. So if we take our payment amount, subtract off the interest that we had to pay, the balance reduction would be $1,801.77 for the second payment. And then to find the unpaid balance, you take the unpaid balance from the previous term, subtract off the balance reduction, and then boom. After the second payment, now we only owe $6,560.26. And then we're going to do this 3 more times. For the third payment, $656.03 goes towards interest. The balance is reduced by $1,981.94. After 3 payments, we'll end up owing $4,578.32. And then after 4 payments, notice less and less is going towards interest, but that's because you're paying down the balance. So now we only have to pay 10% of $4,578.32. That's $457.83. Now $2,000 or $2,180 is going towards reducing the balance. And the balance is down to $2,398.18. And then for the last payment, look how nicely this works out. We have to pay 10% interest on $2,398.18. That would be $239.82. And then our balance is going to be reduced, or well, we paid $2,637.90. So our balance is going to be reduced by $2,398.18. And then look at there, we get down to 0. Excuse me. Okay. All right. So again, this breaks down how much or how each of your payments goes towards interest and goes towards reducing the balance. In the beginning, you owe more than at the end. So in the beginning, you're going to be paying more towards interest with your payments than towards the end. So as time goes on, more of your payment goes towards the principal than goes towards the interest, or goes towards the unpaid balance, I should say, than what goes towards the interest.